break them down, and really get into the core insights, just for you.
Glad to be here.
So today, we're tackling something pretty huge, a real conceptual showdown in modern physics.
Absolutely. It's a clash that really forces us to rethink, well, everything. Reality, space, time.
We're talking about the tension between the two giants of physics, right?
That's it. You've got Einstein's general relativity,
Sure.
gravity, space-time, the big picture stuff, galaxies, the cosmos.
Right, elegant.
Yeah.
Beautiful, even.
And then on the other hand, you have quantum mechanics, the weird, wonderful world of the very small. Particles, forces, incredibly successful in its own domain.
Both have totally reshaped how we see the universe, from like stars down to quarks.
Exactly. But, and this is the big but where these two theories meet, there's this deep, persistent friction. A paradox, really.
And the most famous example of this friction is quantum entanglement.
That's the one. It's a phenomenon where particles get linked up, their fates intertwined, you could say.
Linked how? Like
Yeah.
magnetically.
Not quite like that. It's stranger. If you measure something about one particle, say its spin, you instantly know the spin of its partner. Instantly, even if that partner is light years away.
Okay, instantly is the key word there. That's what bothered Einstein, right? His spooky action at a distance.
Precisely. He found it deeply unsettling. It seems to demand some kind of universal now, doesn't it?
Yeah.
A moment where your action here causes something over there at the exact same time.
Yeah, it feels like it needs that. But didn't Einstein himself kind of demolish that idea?
Yeah.
With special relativity?
He did. Years before quantum mechanics really took shape, his special theory of relativity completely dismantled the notion of absolute time, of a universal now.
It showed that simultaneity, whether two things happen at the same time, isn't fixed.
Exactly. It's relative. It depends entirely on how you're moving, your frame of reference. The universe doesn't have one single clock ticking for everyone.
So two events that look simultaneous to me might happen at different times for you if you're, say, flying past in a spaceship.
Genuinely different times, or even in a different order. It dissolves that intuitive idea of a shared present moment across space.
Wow. Okay, so there's the conflict. Entanglement seems instantaneous, totally connected now. But relativity says now is flexible. It's relative.
That's the heart of the paradox. How can entanglement's instant connection work in a universe where instant is, well, ambiguous, simultaneous? According to whom?
It feels like physics is pulling us in two opposite directions at once.
It does. And look, our goal today isn't to hand you a neat, tidy solution, because frankly, there isn't one yet.
Right.
Instead, think of this as a journey. We're going to explore this dialogue. We'll dig into relativity of simultaneity first.
Okay.
Then unpack entanglement itself. We'll look at the famous EPR debate, the experiments that tried to settle it.
Experimental verdict. Sounds dramatic.
Oh, it was. And we'll see how causality is somehow preserved, look at different ways physicists try to interpret what's going on.
Interpretations.
Yeah.
Like different stories about the same data.
Sort of, yeah. Different ways to make sense of the weirdness. And we'll touch on some really cutting-edge ideas like ER equals EPR.
EPR. Okay, you've got my attention. Let's dive in. Where do we start? Time.
Let's start with time, specifically Einstein messing with it. Because before him, we had the Newtonian view.
Newton. Comfortable, predictable, absolute space, time just flowing the same for everyone everywhere. One big cosmic clock.
Simple, intuitive. We all shared the same net.
And then 1905 happens. Einstein publishes his special theory of relativity.
And bam, that whole intuitive picture shatters. The key takeaway for us today is this relativity of simultaneity.
Right. The idea that two events, separated in space, whether they happen at the same moment isn't a fact, it's a perspective.
It really depends on the observer's motion. What's simultaneous for me might genuinely be sequential for you, one after the other.
That's still hard to grasp. It's not just how things look.
No, it's fundamental. It's baked into the fabric of space-time, and it comes directly from Einstein's two big postulates.
Which were? Remind me.
Okay, first, the laws of physics are the same for everyone moving uniformly. No special viewpoints.
It makes sense.
Second, and this is the kicker, the speed of light in a vacuum, c, is constant for everyone, no matter how fast they're moving or how fast the light source is moving.
That fixed speed of light is the key.
It's the key that unlocks the relativity of simultaneity. Let's use the classic thought experiment. The train and the platform.
Okay, I think I remember this one. Long train, moving fast.
Right. Constant speed. Person B is exactly in the middle of the train carriage. You, person A, are standing still on the platform, also midway as the train passes.
Got it. Train whizzing by.
Now imagine two lightning bolts strike the very front and the very back of the train simultaneously from your perspective on the platform, person A.
Okay. Simultaneous strikes for me, the observer on the ground.
Right. Since you're in the middle, the light from both strikes travels the same distance to reach you. And since light travels at sea...
They arrive at my eyes at the exact same time.
Yeah.
Proof they were simultaneous. Simple.
Yeah. Simple for you. Now, let's jump onto the train with person B. They also see light traveling at sea. That's crucial.
Okay.
But while the light beams are traveling towards person B, the train itself has moved forward.
Right. So the spot where the rear bolt struck is moving towards the light coming from it.
Effectively, yes. The light from the rear strike has less distance to cover to reach person B in the middle.
And the light from the front strike.
Has further to travel because person B is moving away from where that front strike happened.
So even though the light speed is the same, the arrival times will be different for person B.
Exactly. Person B sees the light flash from the front of the train arrive before the flash from the rear.
And since person B knows they're in the middle of their own train,
they have to conclude the front strike happened earlier. It's the only logical explanation from their frame of reference.
So, same two lightning strikes, simultaneous for me on the platform, not simultaneous for person B on the train, and neither of us is wrong.
Neither is wrong. That's the mind-bending part. Simultaneity is not absolute. The universal now dissolves.
How does the math handle this? It can't just be a story.
It's formalized by the Lorentz transformations. These are the equations that tell you how space and time coordinates change between moving frames. There's a term in the time transformation, VXC2, that explicitly shows how spatial separation and relative velocity mix together to create a time difference. Your now literally gets tilted relative to mine.
Okay, tilted nows. And this leads to Minkowski spacetime.
Yeah, Hermann Minkowski realized you could visualize this beautifully by uniting space and time into a single four-dimensional spacetime. Each observer traces a path, a world line.
And their present is like a slice through that space-time, their line of simultaneity.
Exactly. And the Lorentz transformations show that if we're moving relative to each other, our slices, our lines of simultaneity are tilted. There's no universal horizontal now that we all agree on.
Okay, I think I'm getting the relativity part.
Yeah.
So how does this smash head-on into entanglement?
The clash isn't just about things happening faster than light, although that's part of the worry. It's deeper. It's about causality.
Causality. Cause and effect.
Yes. If Alice measures her entangled particle and it instantaneously affects Bob's particle far away, the big question is, instantaneous in whose frame?
Because my instant might be before or after your instant if we're moving differently.
Precisely. If there's no universal now, then for some observers, Alice's measurement might happen first, causing the effect on Bob's particle. But for other observers, Bob's particle might seem to settle into its state before Alice even makes her measurement.
Wait, that sounds like the effect could happen before the cause.
No.
That breaks everything, right?
It would seem to violate causality, which is a very fundamental principle. So the spookiness Einstein worried about isn't just the speed, it's this fundamental ambiguity about when the influence happens and which event causes which. That's the deep tension.
Okay, so that sets up the problem. Now let's pivot to the other side. Entanglement itself. What is it, fundamentally?
Fundamentally, it's a quantum phenomenon where particles become linked. So linked that you can't describe them individually anymore. They behave as a single system.
Even when they're far apart?
Even when they're light years apart. The connection remains. The state of the whole system is what matters, not the individual parts. It's holistic.
And this involves superposition.
Yes. Remember, before measurement, quantum particles exist in a superposition, like being spin up and spin down at the same time. Not just unknown, but genuinely indefinite.
Okay.
Entanglement then creates perfect correlation within that superposition. The classic example. A particle with zero total spin decays into two daughter particles. Conservation laws demand their spins must cancel out.
So if one is measured spin up,
the other must instantly be found spin down, no matter how far apart they are. It's built into the combined mathematical description, often called the spin singlet state. It's like they're two sides of the same quantum coin. Knowing one side tells you the other instantly.
Is this hard to create? Is entanglement rare?
Actually, no. It happens all the time in nature. Conservation laws like spin or momentum naturally lead to it. In labs, techniques like spontaneous parametric down conversion are standard. Shining a laser through a crystal can split photons into entangled pairs.
And quantum computers use it too, right?
Absolutely. Gates, like the CNOT gate, are designed specifically to entangle qubits. It's a fundamental resource in quantum information.
So here's maybe the crucial part you mentioned earlier. We talk about two particles, but maybe that's the wrong language.
I think it really is a language trap. It makes us imagine two little marbles sending secret messages. But the quantum math, the formalism, describes a single entity, a single wave function or state vector that lives in a higher dimensional space representing both particles together.
And this combined state can't be split into particle A's state times particle B's state.
Exactly. If it could be factored like that, they wouldn't be entangled. Entanglement means the description is fundamentally irreducible. It describes the system.
So instead of how does A signal B, we should ask,
Maybe something like, how does interacting locally with one part of this unified, non-local system affect the state of the entire system?
okay, the correlation isn't a message between two things, but a property of one indivisible thing that just happens to manifest in two places when we poke it.
That's a much better way to think about it, I believe. The particles are like, well, localized bumps or measurement outcomes that emerge from this single underlying non-local reality. The connection is the reality.
The dance materializes not from any one particle, but from the connections between them.
I like that. It captures the shift in perspective needed.
Which brings us back to Einstein's discomfort. He saw this, felt this tension, and formulated the EPR paradox.
Right. In 1935, with Podolsky and Rosen, their goal wasn't to say quantum mechanics was wrong in its predictions.
Just incomplete, like he was missing something.
Exactly. They argued it didn't provide a full description of physical reality, and their argument rested on two, very reasonable-sounding classical ideas, locality and realism.
Locality?
Yeah.
No spooky action at a distance. What happens here can't instantly affect something way over there.
Check it. And realism. Things have definite properties whether we look at them or not. The moon is still there, even if nobody's looking.
They even had a definition for that, right? The EPR criterion of reality.
Yeah. If, without in any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to that quantity. Basically, if you can know it for sure without messing with it, it must be real.
Okay, so how did they use these ideas to create the paradox?
They imagined their entangled pair, A and B, flying apart. Let's say their positions and momenta are entangled.
Okay.
Alice gets particle A. She chooses to measure its position. Because of entanglement, she instantly knows B's position perfectly.
Right.
Now, locality says her measurement of A couldn't have disturbed B way over there. So, by the EPR reality criterion, since she can predict B's position with certainty without disturbing it, B must have had a definite position all along.
Okay, makes sense based on their rules. But what if she chose differently?
Exactly. What if Alice decided to measure A's momentum instead? She'd then know B's momentum perfectly. Same logic applies. Locality means she didn't disturb B, so realism means B must have had a definite momentum all along.
So B had a definite position and a definite momentum all along.
That's what the local realism argument implies, but
that contradicts Heisenberg's uncertainty principle. You can't know both position and momentum precisely at the same time in quantum mechanics.
bingo, that's the contradiction. EPR said, since our reasonable assumptions, locality, realism, lead to a conclusion that contradicts quantum mechanics must be incomplete. It's not telling the whole story.
And they propose these hidden variables,
Yeah.
like the gloves in the boxes.
Exactly like the gloves. They suggested maybe particles have hidden instruction sets, pre-programmed properties we just can't see. The apparent randomness of quantum measurements would just be our ignorance of these hidden details. The outcome was fixed from the start, just like the gloves' handedness was fixed when they were put in the boxes.
So for decades, it was this standoff. Bohr's view versus Einstein's view. Measurement creates reality versus reality is hidden.
Pretty much. A philosophical debate, really. No one knew how to test it experimentally, until John Stuart Bell came along in 1964.
The Irish physicist. What was his big idea?
His genius was realizing that the assumption of local realism itself, the idea of pre-programmed hidden variables, actually made testable predictions that were different from standard quantum mechanics.
How could you test something like hidden variables?
Bell derived mathematical inequalities. Think of them as rules that any local realist theory must obey. He showed that if particles carry hidden instructions, there's a limit on how strongly correlated the measurements on particle A and particle B can be, especially when Alice and Bob choose different measurement settings, like measuring spin along different axes.
Okay, so local realism puts a cap on the correlation string.
It does. There's only so much agreement you can get if the answers are pre-written locally.
And then what did he find when he calculated the same thing using standard quantum mechanics?
He found that quantum mechanics predicted correlations that were stronger than Bell's limit. Quantum mechanics violates the Bell inequality.
Whoa. So they make fundamentally different predictions for the same experiment.
Yes. This was huge. It meant that local realism and quantum mechanics were incompatible. The universe couldn't be both. Nature had to choose. And for the first time, there was a clear experimental question you could ask to find out which description was right.
Okay. The stage is set for the experiments, the Bell tests.
Exactly. Starting in the 70s, physicists began designing experiments to measure these correlations and see if they obeyed Bell's inequality, meaning local realism was right, or violated it, meaning quantum mechanics was right.
And this led to the Nobel Prize in 2022 for Clauser, Aspect, and Zeilinger.
That's right. Their pioneering work was crucial. Clauser, with Friedman, did one of the first convincing tests back in '72, showed a clear violation favoring quantum mechanics.
And Aspect.
Alain Aspect's experiments in the early '80s were particularly significant. He used fast switches to change the measurement settings while the entangled photons were already in flight.
Why was that important? To close loopholes.
Precisely. Early experiments, while suggestive, had potential loopholes that a determined defender of local realism could point to. Aspect's setup was designed to close the locality loophole, the worry that the detectors might somehow be communicating faster than light or coordinating based on information from the source. By changing settings super fast while the particles were separated, he made that kind of explanation much harder.
Were there other loopholes?
Oh, yeah. Physicists are clever and skeptical. There was the freedom of choice loophole. Maybe the choice of measurement setting wasn't truly random. Maybe it was somehow correlated with the hidden variables themselves in a grand cosmic conspiracy.
Seriously, that sounds far-fetched.
It does. It's called superdeterminism. But to rule it out rigorously, experiments used increasingly random sources for the settings, even light from ancient, distant quasars billions of light years away. The idea was to make any conspiracy have to stretch back billions of years.
Wow. Okay, what else?
The detection loophole. Early detectors weren't very efficient. They missed a lot of particles. So maybe they were only detecting a biased sample that looked like it violated Bell's inequality, but the full set wouldn't.
So they needed better detectors.
Exactly. Developing high-efficiency detectors that could catch almost every particle was key to closing this loophole.
And all this culminated in 2015, the loophole-free tests.
Yes. Several groups independently performed experiments designed to simultaneously close all the major loopholes: locality, freedom of choice, and detection. It was a huge experimental effort.
And the result? Drumroll.
The results were crystal clear, overwhelmingly decisive. Every experiment showed a profound violation of Bell's inequalities. Local realism, as Einstein, Podolsky, and Rosen envisioned it, was definitively ruled out.
How certain are we? Like statistically?
Ridiculously certain. One group reported ruling out local realism with 11.5 standard deviations. The chance of that happening randomly in a local realist universe is less than 1 in, 10 to the power of 30. It's basically 0.
So it's settled. The universe is non-local. That intuitive clockwork picture is just wrong.
Experimentally, yes, the verdict is in. Nature is non-local. That classical view of separate parts interacting locally just doesn't hold up at the fundamental level. Reality is interconnected in a way that defies classical intuition.
That's a massive shift in worldview. It's not just physics, it's philosophy.
It absolutely is. It forces a reckoning. Non-locality isn't just a weird theoretical possibility. It's an experimentally established fact we have to incorporate into our understanding of the universe. Any future theory has to account for it.
Okay, but wait. If things are non-locally connected, doesn't that bring us right back to the faster-than-light communication problem? And paradoxes, breaking relativity.
It seems like it should, right? But here's where quantum mechanics pulls another rabbit out of the hat. The no communication theorem.
A theorem that says no signaling.
Exactly. It's a mathematical proof within quantum mechanics itself. It demonstrates that while entanglement involves non-local correlations, you absolutely cannot use those correlations to send information faster than light.
How does that work? If Alice measures hers and Bob's instantly changes state, Why can't she send a Morse code or something?
Okay, think about Alice trying to send a 1 or 0 to Bob. She measures her particle's spin. Let's say she wants up to mean 1 and down to mean 0.
Right.
Here's the crucial part. Quantum mechanics says her measurement outcome is fundamentally random. She gets up 50% of the time and down 50% of the time for a maximally entangled state. She cannot force the outcome. She can't decide, I want to measure up now to send a 1.
Ah, so she can't control her side of the transmission.
Precisely. Now, let's say her random outcome is up. Bob's particle, far away, instantly becomes down due to the correlation, but Bob has no idea this has happened.
Why not? His particle changed state.
From his perspective, before he measures, his particle is just part of an entangled pair. Its state is indefinite to him. When he measures it, along the same axis as Alice, he will find down with 100% certainty in this specific instance.
Okay.
But if Alice had randomly measured down, which happens 50% of the time, his particle would have become up and he would measure up. Since Alice's results are perfectly random, 50-50, but his own measurement results, averaged over many trials without knowing what Alice did, will also be perfectly random, 50% up, 50% down.
So Bob just sees random noise on his end. He can't decode anything from it.
Nothing at all. His data stream looks completely random. The perfect anti-correlation between his results and Alice's results only becomes apparent later when they compare their data using a normal, slower-than-light channel like email or a phone call.
That's clever. So the spooky connection is real. It affects Bob's particle, but it does so in the dark, statistically hidden.
Exactly. It changes the underlying probabilities instantly, but in a way that produces no discernible pattern locally for Bob. Nature allows the non-local connection, but forbids using it to break causality or send signals faster than light. It's a kind of peaceful coexistence between quantum weirdness and relativity.
Okay, so the experiments say non-locality is real, but the no communication theorem says we can't use it to send messages. That answers the what. But it still doesn't answer the how, does it? How are these correlations actually maintained across space?
You've hit the nail on the head. The standard quantum formalism tells us the rules, predicts the outcomes, but it doesn't really provide a satisfying story about the underlying mechanism, and that's where the different interpretations of quantum mechanics come into play.
These aren't different theories, right? They predict the same results.
Correct. They all agree on the experimental predictions, but they offer vastly different pictures, different metaphysical frameworks for what's actually happening behind the curtain.
Okay, let's hear about them, the main ones. Copenhagen first.
Copenhagen is the oldest, kind of the default interpretation for many physicists. Here, the wave function, the mathematical description, isn't seen as a real physical thing, but more like a tool representing our knowledge about a system.
So properties aren't real until measured.
Essentially, yes. Properties like spin are indefinite until you perform a measurement. The act of measurement forces the system out of superposition and into one definite state. This is the infamous collapse of the wave function.
And for entangled particles, this collapse is instantaneous and global.
That's the standard Copenhagen picture. Alice measures her particle, and the single wave function describing the entire entangled system collapses instantly everywhere. Bob's particle snaps into a definite state because it was part of that collapsing system.
But that sounds like it brings back the simultaneity problem with a vengeance. Collapse has to happen now. Whose now?
Exactly. That instantaneous, apparently a causal collapse is where Copenhagen feels most uncomfortable when you try to reconcile it with relativity's frame-dependent time. It seems to demand a special, privileged frame of reference, which relativity denies.
Okay, so that's one view. What about many worlds? Sounds dramatic.
It is. Proposed by Hugh Everett III. MWI takes a completely different tack. It says the wave function is objectively real. And crucially, it never collapses.
Never collapses. So what happens when Alice measures her particle?
Measurement is just a normal physical interaction. It causes the observer, Alice, to become entangled with the system she's measuring. And this entanglement causes the universe itself to branch.
Branch into parallel universes.
Essentially, yes. All possible outcomes of the measurement actually happen, each in its own separate branch, its own world.
So if Alice measures spin?
In one branch, she measures up, becomes Alice who measured up, and in that world, Bob's particle is down. In another branch, totally separate and non-communicating, she measures down, becomes Alice who measured down, and Bob's particle is up.
So the correlation is preserved perfectly within each branch.
Exactly. There's no spooky action at a distance because nothing travels between branches. The correlations were inherent in the universal wave function from the start. Measurement is local. It just determines which branch the observer finds themselves in. Apparent randomness is just your subjective experience of being in one branch and not seeing the others.
Does MWI have the same tension with relativity?
Much less so, because there's no instantaneous collapse happening across spacetime. All interactions in the branching process itself are considered local.
Interesting. Okay, one more. Pilot wave theory.
Also known as Bohmian mechanics, this one actually is a hidden variables theory, like Einstein wanted, but crucially, it's explicitly non-local. Bell's theorem didn't rule out all hidden variable theories, just the local ones.
So how does it work? Particles have definite properties.
Yes. In Bohmian mechanics, particles always have definite positions, the hidden variables. What we call the wave function is a real physical pilot wave that literally guides the particle's motion. It's fully deterministic.
Okay, so where does the non-locality come in? How does Alice affect Bob?
It's built right into the guiding equation that determines how the particles move. A particle's velocity at any given moment depends on the instantaneous positions of all other particles in the configuration described by the pilot wave, no matter how far away they are. Instantly. So when Alice measures her particle, which involves interacting with it, changing its position, this instantly changes the global pilot wave. And that instantly changes the calculated velocity and trajectory for Bob's distant particle, ensuring the correlations match quantum predictions.
So the spooky action is a real faster-than-light influence via this pilot wave.
Yes, it's a direct, causal, non-local connection. But because it's instantaneous, it runs headlong into the spirit of special relativity. It seems to demand a preferred frame of reference, a special slice of simultaneity for this guiding influence to propagate instantly across, even though it's cleverly constructed to prevent faster-than-light signaling.
So Copenhagen has tension with relativity due to collapse. Many worlds avoids it by branching locally, and pilot wave embraces non-locality but needs a preferred frame. Quite different takes.
Radically different pictures of reality, all consistent with the same experiments, at least so far.
This whole discussion, it really goes beyond just physics equations, doesn't it? It hits our fundamental ideas about how reality works.
Absolutely. The experimental proof against local realism is a watershed moment. It forces us to confront assumptions we barely knew we had about space, time, cause, effect, and interconnectedness.
That old mechanical view of the universe, little separate parts bumping into each other locally, it's just gone.
The Bell tests hammered the nails in that coffin. The universe, at its deepest level, seems to be holistic, interconnected, a web, not just a collection of marbles. That demands a philosophical shift.
And this shift is opening up new frontiers, like trying to connect quantum mechanics and general relativity.
Yes, finding a theory of quantum gravity is the holy grail. And some of the most exciting, though speculative ideas are emerging right at this intersection of entanglement and spacetime geometry, like the ER-EPR conjecture.
Okay, let's unpack that. ER-EPR conjecture.
ER refers to Einstein-Rosen bridges, which are basically wormholes, theoretical tunnels through spacetime predicted by general relativity. EPR refers to Einstein, Podolsky, and Rosen, and their entangled particles.
So wormholes equal entanglement. How?
The conjecture, put forward by Maltesina and Susskind in 2013, suggests that maybe two entangled particles are literally connected by a microscopic wormhole, a tiny Einstein-Rosen bridge.
Wait, really? Like a physical tunnel?
In this picture, yes. The idea is that the spooky action isn't some mysterious influence traveling through space. Instead, the entanglement is the connection. It is the wormhole. The particles are like two mouths of the same tunnel.
So the correlation isn't happening across space, it's happening through this shortcut outside of normal space.
Sort of. The wormhole itself is part of the space-time geometry. The non-local correlation we see is just a manifestation of this underlying geometric link. It reframes the whole problem.
That's mind-bending. What are the implications if that's true?
The biggest implication is potentially revolutionary. It suggests that space-time geometry itself might not be fundamental. It might be emergent.
Emergent from what?
From the network of quantum entanglement. The idea is that the smooth fabric of space-time we experience is somehow sewn together or built up from these more fundamental quantum connections, these ER bridges. Entanglement might be the thread that weaves space-time.
So instead of entanglement happening in space-time and conflicting with it, space-time might be made of entanglement.
That's the radical proposal. It flips the whole relationship on its head. And if true, it could be a huge step towards unifying gravity and quantum mechanics, maybe even solving other deep puzzles like the black hole information paradox.
Of course, you said this is speculative.
Highly speculative. It's very much an active area of theoretical research, but it shows how deeply physicists are rethinking foundational concepts in light of entanglement and non-locality.
It suggests the resolution to this clash between entanglement and simultaneity might not be tweaking one theory or the other, but finding a deeper level where they are unified.
Perhaps. Maybe entanglement and spacetime geometry are in conflict, but are two aspects of a single, deeper structure of reality woven from these quantum connections.
It certainly leaves you with a lot to think about. The idea that the space around us, the very fabric of reality, could be built from these spooky links
It changes how you look at things, doesn't it? How connected everything might truly be.
definitely gives us something to ponder. Thanks for taking us through this deep dive.
My pleasure. It's fascinating territory.